Wanted to work through a problem that involves capacitors. It's a problem that doesn't involve a complicated numerical calculation, but it is a problem that involves a difficult thought process. So let's take a look at this problem. Upstairs on the whiteboard, I pictured two capacitors. There's one on the left, C1, there's one on the right, C2. The one on the left is a 13 microfarad capacitor. The one on the right is a 48 microfarad capacitor. So the one on the right has more capability of storing charge. The one on the less capability of storing charge. They're both initially connected to 25-volt batteries. So they're both connected to the same potential difference. And because of that 25 volts, charge is stored on capacitor C1. Charge is stored on capacitor C2. It's going to be more on C2 than on C1 because capacitance of C2 is larger. Capacitance of C1 is smaller. In the picture upstairs, over here on the left, I actually figured out how much charge. And I figured out how much charge is stored on the plates of the capacitor C1 just using the law that the capacitance of a capacitor is the charge divided by the voltage and rearranging that. I did the same thing for this second capacitor, C2. I figured out the charge that's stored on the second capacitor. Again, I just did it by rearranging the law that C, the capacitance, equals charge over voltage, and rearranging it for the charge. And the smaller capacitor we see is storing 325 microcoulombs for 25 volts. The larger capacitor is storing 1200 microcoulombs for 25 volts. Then we're told an interesting thing. We're told that we're going to disconnect the two capacitors from the battery. And then we're actually going to connect the two capacitors together, meaning, terminal of one capacitor connected to a terminal of the other capacitor, and then the two remaining terminals of the two capacitors connected together. So we're going to reconnect them, but we're going to reconnect them in a particular way. We're going to reconnect them such that the positive terminal, the one storing positive charge of one capacitor, is connected to the negative terminal storing negative charge of the other capacitor, and vice versa. That's one of two possibilities. We could connect positive to positive for the two capacitors and negative to negative, but we connected positive to negative and negative to positive in this rearranger. And the question is, what is the question we're going to answer? What is, after reconnecting the two capacitors, what is the voltage between the two capacitors? The voltage across the plates of each of the two capacitors, and what is this charge stored by the two capacitors? How much charge is on C1? How much charge is on C2? We're going to discover, the voltage on between the plates of the two capacitors is not going to be the 25 volts that we started with. The charge on the plates of the capacitor, it's not going to be 30 microfarads for C1 and 48 microfarads for C2. So something's changing when we reconnect the two capacitors, plus the minus and minus the plus. And we're going to explore that change, try and understand that change, and figure out how much charge remains on C1 and C2. What is the potentials between C1 and C2? To start this off, I'm going to redraw this sketch over here at the bottom. I'm going to redraw this sketch with the two capacitors connected together. To start this off, I've drawn the two capacitors. C1 is upstairs here, and C2 is downstairs here. At the moment before, I arrange that the negative terminal of C1 is attached to the positive terminal of C2, and the positive terminal of C1 is attached to the negative terminal of C1. So this is the moment before I make the connection. And I'm just looking at the situation of the two capacitors before that moment. Now, for C1, I would see the charge of minus and plus 13 microfarads on the two plates. And for C2, I would see the charge of minus and plus 48 microfarads on the two plates. So those would be the charges. I just labeled them Q1s and Q2s, plus Q1s, plus Q2s, minus Q1s, minus Q2s in my little figure here. And the other thing I've noticed is that there's a potential difference between the two plates for C1. And with the negative terminal on the left, I've written that as 0 volts, and the positive terminal on the right at 25 volts. That's the potential difference between the plates. And for the other capacitor, C2, it's reversed. So it's got 25 volts more positive on the left, 0 volts on the right. And that's just because we're connecting minus to plus on the left-hand side, plus to minus on the right-hand side. Now, what's going to happen when we connect together, the moment we connect together these two capacitors? Let me draw that. So here's my picture after connecting together the two capacitors. Now, when I connect together the two capacitors, there's an important point. I'm connecting together on the left-hand side, this wire here joining the two capacitors on the left-hand side. I'm connecting together one end of the wire that's at 0 volts and the other end of the wire that's at 25 volts. And this is a conductor, remember, and conductors in equilibrium have the same potential. And so we got a conductor that's not in equilibrium because there's 0 volts upstairs here and there's 25 volts downstairs here. So there's a potential hill on this capacitor, and that will cause charges to move through this wire. And because electrons roll up a potential hill because they're negatively charged, I've drawn the electrons rolling up the potential hill from the negative plate of C1 to the positive plate of C2. So this charge is going to immediately start flowing around on the left-hand side of this circuit. And so that's what I'm indicating here with this flow of electrons. Similar thing happens on the right-hand side. On the right-hand side, I've connected the 25-volt positive terminal of C1 to the 0-volt terminal of C2. So again, I've made a situation where I've got a conductor that doesn't have constant potential. So it's not in equilibrium. When a conductor is not in equilibrium, where the potential is not constant, that's going to cause charges to move through, the electrons to move through the conductor. Since C2's negative plate is downstairs here on the right, electrons are going to roll off, pour off that plate, and run round over to this plate of the positive plate of C1. And so here I've indicated, again, electrons moving around. So the key thing in this picture is the moment I connect these guys up, C1 and C2, I've got electrons pouring off the negative terminal of C1. I've got electrons pouring off the negative terminal of C2. What's going to happen is we're going to neutralize some of the charge on the plates of the capacitors. What we don't change, however, and I'm trying to stress it in my diagram here, is that the total charge that's over on the left-hand side of this circuit, and that total charge is the minus Q that started on the left-hand plate of C1 and the plus Q that started on the left-hand plate of C2. That's not going to be changed. This total charge on this wire and these two plates is not going to change. It's just going to be redistributed. And likewise over here on the right-hand side, although we've got electrons flowing from the lower plate to the upper positive plate, we're redistributing the charge. We're not going to change the fact that there's a total amount of charge plus Q1 minus Q2 that's located somewhere on the right-hand side of the circuit. We're just redistributing that charge. And really, this whole problem is about how do we redistribute the charge? In what way, in what proportions do we redistribute the total charge that's on the left-hand side, the total charge that's on the right-hand side? The key to understanding how we redistribute the charge is the following important point. Again, once we reach equilibrium, this wire and these two plates on the left will all be at the same potential. Once we reach equilibrium, this wire on the right and the two plates on the right, they'll all be at the same potential, so that there'll be a constant potential, and I can draw it here, between the left-hand side of the circuit diagram and the right-hand side of the circuit diagram. And we'll just call that V. To find this constant voltage between the left-hand side and the right-hand side of the circuit, which is the voltage across C1 and is the voltage across C2, I'm going to replace the arrangement here of two capacitors with a single equivalent capacitance. And so I'm going to use the rules for combining capacitors in parallel to rewrite or replace the two capacitors, C1 and C2, with a single equivalent capacitance. The rules for a parallel circuit of capacitors is just that the equivalent capacitor is the sum of the individual capacitors. And then I'll figure out the voltage across the plates of this single capacitor, knowing its capacitance and knowing the total charge that it's storing. Now, at this point, you might say, well, why did you decide that this circuit in the center here of the two capacitors, C1 and C2, why did I decide that that's parallel? Maybe I could have looked at it and said, well, it looks more like it's series to me. And actually, that circuit is kind of ambiguous. You could think of it in a way in which C1 and C2 are parallel to one another. You could also think of it in a way in which C1 and C2 are in series to one another. So why did I pick that it's a parallel circuit over a series circuit? My reasoning is the following. We figured that the voltage across C1 and C2 is the same in this circuit. Otherwise, if it wasn't the same, the conductors wouldn't be in equilibrium and charge would move until it was the same and the conductor was in equilibrium. So we figured that the voltage must be the same across C1 and C2. We also recorded that the two capacitors in this circuit here are sharing this amount of charge. They're sharing this charge that I rewrote over here as plus and minus the difference between Q2 and Q1. So in this circuit, when we look at it, we see that it's got the same voltage across the plates of the capacitors, but it's sharing the total charge between the two capacitors. And that's the characteristic of a parallel arrangement of capacitors. That has the same voltage across the plate. It shares the charge. That means it has the same voltage across the plates as the equivalent capacitor, and it shares the charge that's in total stored by the equivalent capacitor. That's quite different than a series circuit. In a series circuit, the two capacitors would share the voltage, and the two capacitors would have the full charge on each of their plates. So that's why I made the decision that this is a parallel circuit. Okay, so at this point, we've got our final circuit diagram here. If we look at this circuit diagram, it contains a single capacitor, the single equivalent capacitance, and we actually know that value because it's just going to be the sum of the 30 microfarads and the 48 microfarads. So this is 61 microfarad capacitance. And we just want to figure out this voltage that's across the plates of that capacitor, and also it's going to be the voltage across the plates of these two capacitors arranged in this parallel arrangement. And we can figure this voltage because actually we also know this charge that's on the plates of the capacitors on the left-hand side and the right-hand side, because it's Q2 minus Q1. So Q2 was 1200 microcoulombs. Q1 was 325 microcoulombs. So that means the difference, that's 875 microcoulombs. That's negative 875 on this side of the capacitor, on the right-hand side, and it would be plus 875 microcoulombs of charge on the left-hand side of the capacitor. So we're in a situation that's relatively straightforward now, where we know the charge on the plates of a capacitor, we know the capacitance of the capacitor, we just got to find the voltage. So now it's just a matter of doing the calculation. And so let me go ahead and do that. The voltage across the equivalent capacitor, I'll just call it V, which we noted is the voltage across the two individual capacitors. So it's also equal to V1. It's also equal to V2, can be written with that law that describes a capacitance in terms of the capacitance and the charge on the plates of the capacitor. It will be Q2 minus Q1, that's the charge on the plates of the equivalent capacitor, divided by the capacitance of that capacitor. So that's a C equivalent that we already wrote down. And so this is just 875 microcoulombs. That's the charge on the equivalent capacitor, divided by the equivalent capacitance, that was 61 microfarads. And if I divide one by the other, that comes out to be 14.3 volts. So now we know we got 14.3 volts across the equivalent capacitor. We've also got 14.3 volts across C1 and C2. Remember, we started with 25 volts, but remember we redistributed the charge because the wires on the left and the wires on the right were not in equilibrium. And so we redistributed charge. We actually reduced the amount of charge on the plates of the capacitor. That reduced the potential differences between the plates of the capacitors. We reduced it down, it turns out, from 25 volts down to 14.3 volts. Now we also want to figure out the charge on each of the two capacitors, C1 and C2. So Q1 will now be, again, by the law of the capacitance, that C equals Q over V, so that Q equals CV. In this case, Q1 will be C1V, V1, and we just got to fill in the values. So we just got to fill in here that the capacitance C1 is 13 microfarads. The voltage across its plates are now just 14.3 volts. And if I multiply these two numbers together, I get the charge on the capacitance C1, and that came out to be 186 microcoulombs, sorry. And we could do the same thing for the second capacitor, C2. So the charge on its plates, I'll call it Q2 again, that's going to be its capacitance, C2, times the voltage across its plates, V2. C2 is the 48 microfarads. I'm running out of space, so I won't write the number in. V2 is the 14.3 volts again. So we got 14.3 volts times 48 microfarads. That number comes out to be 689 microcoulombs. And so here at the bottom is the answer to our problem. When we reconnect these two capacitors together, the question was, how does the charge redistribute? How does the potentials between the plates change? We saw that the charge would redistribute because our capacitors are no longer in equilibrium. We saw that the charge would redistribute so that it lowers the amount of charge on the plates. It lowers the potential between the plates because I had connected positive to negative ends of the two capacitors. And when we calculated the whole thing out, we got this result here. If we look at the numbers, the original 25 volts across the capacitors went down to a little over half that, 14.3 volts. The charges that were stored by the capacitors, well, for C1, it went down from 325 microcoulombs down to 186 microcoulombs, and for C2 it went from 1200 microcoulombs to 689 microcoulombs. So that's also correspondingly down by nearly one half, not quite one half. So that's a problem that, in terms of the mathematics, we just use C equals Q over V, and we just repeatedly used C equals Q over V. But the mathematics was not the problem with this problem. What was the problem with this problem is it's tricky to reason out what's happening. So we had to think very carefully about what's happening. That's why I went rather laboriously through first imagining on the left here the moment before we connect together the terminals of the two capacitors. This is when we still got 25 volts between the plates of each capacitor, and we've still got the original charges of 325 microcoulombs and 1200 microcoulombs on the plates of the capacitor. And then we touched together the terminals on the left-hand side, connected them, touched together the terminals on the right-hand side. We suddenly realized that we're connecting 0 volts to 25 volts on the left, 0 volts to 25 volts on the right. That's putting conductors in non-equilibrium. That's creating a potential hill. That's going to cause charges to flow until that potential difference between the top and bottom wires on the left, top and bottom wires on the right is canceled out by redistributing the charge. So we saw the electrons stream around from the capacitor C1's left-hand plate, stream around from capacitor C2's right-hand plate to try and equalize the potential along the left-hand wire and the right-hand wire. To find out what that potential was, what we said is, let's imagine that this two capacitor circuit can be replaced by a single capacitor. It's a single capacitor with the same potential across the plates, single capacitor that's storing the same amount of charge, total charge, as the left-hand and right-hand parts of this circuit. We were using the rules for a parallel arrangement of capacitors because we spotted those were the right rules for this case, where we're going to have constant potential, the same potential across C1 and C2. And so it's a parallel arrangement. We were going to share the charge, this charge here, this charge over here on the right, between C1 and C2. Again, that's a rule for a parallel arrangement of capacitors. Once we had replaced the pair of capacitors C1, C2 with an equivalent capacitance, and once we realized, of course, we know the charges on its plates, we know the capacitance of the equivalent capacitor, it was easy to find the voltage. And that was the voltage on C1 and C2. And then it was easy to find the charge on C1 and C2 because we know the capacitance of C1 and C2. Well, that problem is quite a mouthful in terms of explaining it, understanding it. But it really gets us into the depths of understanding capacitors, understanding potentials and charges on plates of capacitors. And so that's why we explored that problem.